Alright, I'm coming to you from the studios of the very strange. um, I had a terrible time yesterday. I was so depressed because I thought I really lost the knack, the gift, or no, I lost self-confidence in my ability to come up with free energy circuits because I thought, well, gee, I depend on these simulators to create my reality. And I know they're slightly make-believe. I try to change the software code of Paul Falstad's simulator to make it as realistic as possible. But I had a really bad experience yesterday with three different simulators: Paul Falstad's, uh, Microcap, and LT Spice. And this one, oh, there you go, Microcap. Um, and it led me to believe that Microcap is a mixed blessing. It basically it has policy to suppress surges, but it also is very reasonable in dealing with resistances. And LT-Spice is not reasonable, nor is Paul Falstad's electronic simulator, which you see a version of here that I've modified in various ways. Um, because I stacked 1 ohm resistors in parallel, and the more I added in parallel, the more current became magnified within the entire circuit, despite the fact that I had resistances elsewhere in the circuit of a fixed value, which should have prevented the magnification or amplification of current. Now, in Microcap, they kept a limit of around, I was putting out a 600 amp limit, which makes sense because the more resistors of 1 ohm, the more 1 ohm resistors that are added in parallel, the overall resistance, as you know, keeps dropping because of current division. But in LT-Spice and Paul Falstad simulator, that little microcosm, that little sub-circuit, was taking over the rest of the circuit, in a sense that the current generated in that little sub-circuit infiltrated the rest of the circuit, despite the fact that the resistances in the rest of the circuit were stable. They were not changing. And so as I added more 1 ohm resistors in parallel with each other, let me show you what I had. It should not have made any difference. Maybe there's something I don't know about this kind of thing, but it should not have made any difference at all. Is this? No, this is not it. Wrong file name. Let's see. Where are we? Where are we? Where are we? Here we go. So I had all these resistors in parallel here, and it boosted the amps in LT-Spice, and also I have another version in Paul Falstad's simulator. Despite the fact that these resistances here, all these solder joint resistances and the coil and the capacitors, whatever, they're fixed, right? And they add resistance in series. So it doesn't matter what the equivalent series resistance of all these parallel resistors are, in as much as they keep dropping. The more I add in parallel, the singular series resistance equivalent to all these parallel resistors. It doesn't matter if this keeps dropping. Once it drops less than the highest value of resistance elsewhere in series with the circuit, in series with this elsewhere in the circuit, that other resistance should override this, right? Because this is like a fraction of that and should not contribute a whole lot of resistance. It should not take the current that when you have water flowing through a river and you divide it up into equally sized channels, multiple channels of equal size, sure, it'll speed up, but then it'll log jam when it gets joined back together again into a singular flow. It's just like traffic You know, we tend to speed up when we see less cars in front of us, and we tend to slow down when we're bumper to bumper, when there's tons of cars, when it becomes a parking lot on the street. And if the cars should, if 9 out of the 10 cars should disappear suddenly, we'd speed up, right? And if those 9 cars returned, we'd slow down real quick, probably slam on the brakes. So it didn't make any sense, unless I'm mistaken. It makes no common sense. Now, common sense is a fallacy of logic, one of the 5 major fallacies. Appeal to authority and appeal to emotion are 2 others, and those 3 are very popular in our culture. So I hesitate to say that I know what I'm talking about. But in terms of common sense, it did not make any sense that this sub-circuit here, section, should override the rest of the circuits. So I threw away all of this, and then I started making circuits just based on other parameters changes to see what I could do. And eventually, I ended up with a circuit that was so simple that it defied all the flamboyancy and the hope that I had in that in this one. And that is, all I needed was a 10 ohm resistor and a diode and a mains connection, and I was severing myself half each cycle, thinking to myself, oh, what a smart boy I am. I'm participating only in the negative side of an AC cycle, and I'm suppressing the positive side. So that means I'm really smart because I'm sending back energy to the grid, and I'm not taking any amps. Well, I'm sending current back to the grid. I'm not taking any current from the grid, even though I'm borrowing the voltage all the time throughout the entire cycle. Because you'll see here when we run this. But that's a stupid assumption, because it assumes, see, here's the mains, 14 or 13, no, 12 amps negative going back to the mains. The diode is consuming 12 amps positive. You know, the watts sent back to the mains is 1.5 kilowatts. And I had this plugged into an outlet, so I didn't have 240. I had 120 volts. But it doesn't make any sense. I thought, oh, I'd rig up a tiny little simple little circuit to beat the power meter. Yeah, right. It's fraud. I was fooling myself. Because when you look at it, an electromechanical water ammeter, the little disc that spins, the old kind, it spins because of eddy currents. It spins because the AC cycle is actually a spiraling current flowing down the wire. And if we only use half of that spiral, not the entire spiral, it's still going to create an eddy current in the spinning disk of the electromechanical water ammeter half each cycle. Which means, you know, it's like when you're rowing a boat, you don't put your oars in the water the entire time. You lift them out for half of each stroke instead of the full stroke. What difference does it make? So you'll be paddling half as fast, you know? You know, it's so phooey, it's unbelievable. So I kidded myself, and it was microcap that brought me to my senses. Unfortunately, I've done other circuits a year ago or so in microcap, which actually suppresses surges. I've seen it happen just by reducing the time step, and I was able to locate the problem. The surge did happen, but it didn't last before it was suppressed, and then it was just suppressed for the rest of the duration of running the circuit simulation. So I know they have a policy, and they admit it in their help file. You look up convergence errors, I believe it's called, or divergence errors. I think it's convergence. You look up convergence, and you look up the error in the error file, and you'll find they talk about divergence errors, even though you have to look up convergence to find it. And they actually admit that they monkey with your output, and you don't even know about it. You know, the circuit doesn't tell you. They just tell you in the help file who's going to look. And that microcap is the standard in the lab section of electrical engineering at, I believe it's Manitoba University. in Canada. So it just gives you an example. Microcap is considered industry standard. So that gives you an example of how manipulated is our teaching of electrodynamics. If you don't think it's true, just look at how the standard simulator is manipulated. Now, it's true, it did make an intelligent choice for me, and it did not allow a bunch of parallel resistors to take over the circuit. So it did do something. It acts like artificial intelligence. It makes decisions, but sometimes those decisions are not based on intelligence. They are based on policy. Policy has nothing to do with intelligence unless you think you're very smart, manipulating people into a pigeonhole of getting paid and doing the right thing in order to get paid. And the right thing is the policy choice that they have to go along with, not to encourage surges. And that's why I find fault with it and stay away from it. But I had to go to it because I didn't know what I was doing. And so it did wake me up to what I was doing wrong, and then I had to redesign the circuit, and here it is. And it's based, this is like my lightning oscillator in that it builds up a tremendous voltage in order to reap any gain at all. You end up with gigavolts over here. Let me show you if I can see it here. 300 gigavolts over on the circuit side, on this piece of wire. The components don't accumulate that much voltage, but this piece of wire does. Just to get 30 amps over here and 15 amps, or 20 I should say, just under 20 amps being returned to the grid, you have to build up 300 gigavolts. That's dangerous, obviously. But it was the only way to get this circuit to work. Now, the circuit components are very simple. 10 microhenry size coils on the two transformers. The two transformers have a coupling coefficient of 99%, and they are isolation style in the sense that it's a 1-to-1 ratio between the primary and the secondary. The capacitors, 4 of them, 75 picofarads each, 100 micro-ohm solder joints, and then 100 mega-ohm resistor here and here to initiate a charge on the circuit to get it to build up. And once it builds up, regulated here by this clock timer that's running at 360 cycles per second at 1% duty cycle. In order to close these switches only 1% of the time, but 360 cycles per second, so that's a third of a 60 cycle, hertz. So I had to do that in order to shorten the 1%, because I can't reduce the 1% duty cycle any further to like a third of a 1%. But I get to work around that, I increase the cycle time by a factor of 3, from 60 to, by a factor of 6. Oh no, I think it was a factor of 4. Let's go back to the circuit. Let's see. Look in the lower right, 240 hertz, excuse me. So it's 1/4 of a 60 cycle 60 cycles per second cycle. 1/4 of a 60th of a second is the cycle time of this clock, putting out 1%. So it's 1% of 25% of 1/60th of a second is the amount of time these switches are allowed to close and allow a surge to develop. And so the development of the surge takes a long time, but in my time, in real time, because it is a 10 microsecond time step on this simulated circuit. But in real time, it's like 1 1/4 seconds, as we see here. No, this is 2 seconds. It took 2 seconds. Yeah, because I had to jimmy back and forth. So it took a little extra time. So it's probably less than 2 seconds. To reach 200 gigavolts is the target voltage in order to have a little over 12 amps negative drain back to the mains. Now this is DC drainage, unfortunately. That's another caveat. So you got one caveat is humongous gigavolts, 200 gigavolts built up here, in order to send back a mere 12 amps to the grid. The beauty of that, though, is that it takes forever to suffer any appreciable loss. So that's 2 seconds it took or less. 2 seconds or less to build up a surge here using this very specially designed clock timing. And very reasonable coils. 10 microhenries is, not terribly big. And capacitors, 75 picofarads, very easy to acquire. I have a few myself, a friend gave me. But look, see what happened. Then I went to 2 seconds, and I'm still waiting for this to drain. Now, it dropped down to 12.4 amps from the initial amount of 12.42, negative. Well, yeah, both negative. This is just 12.4. And then it stayed there for the longest time. So I increased the time step, and that changed the output slightly. Now it's 19.69-ish. But now I got to see a droppage. So over here on the left-hand side, it's reading negative 19.69. And over on the right-hand side, it's showing up here, it's already dropped to negative 19.65. So 4% of an amp it has managed to drop. We're using 100 seconds time frame. But 11 megaseconds? So I did the math. What is 11 megas? 10, what's 1 megasecond? What's 1 megasecond? It's 277 hours. Times 10? All right, so times 10. Then I divided by 24 hours, and I got 11 and a half days. So if you multiply by 10, because that's what we actually have down here, that's actually not 2 weeks. That's actually 20 weeks, which divided by 4 weeks in a month is 5 months. You got to wait 5 months to see a 4% drop of per amp if you're putting 20 amps back onto the grid non-stop. But it's DC. You're not going to be able to run anything off of this unless it's light bulbs, because it's DC, it's not AC. Non-motor loads, anything does not involve a motor, such as your refrigerator involves a compressor motor, so you're not going to be able to run your refrigerator. So that's why I chose to keep to hopefully under 15 amps, but I didn't change this 240 volts. I should change this to 120. Because this is assuming you only do it on one branch, and that you can get away with, sending amps back to the grid. So I'm going to have to change this part of the circuit. So that part is a little faulty in my thinking. But I had to go to a 100-second time step to be able to, and 10 megaseconds to be able to see any appreciable loss, because this voltage is huge. This is like a battery pack of 300 gigavolts. I'm saying this with emphasis because, this is really remarkable. But it's also dangerous. Sight unseen, for very good reason I say that. So now I'm going to show you, I'm going to run you through how to run the circuit, because you get all these switches to deal with, and how are you going to know what to do? It's probably going to be jumpy, so I'm probably going to have to slow down the time frame here, or the speed, the simulator speed, because I'm running a screencast at the same time. So 2 weeks. So actually, it's not, this is something else I have to change. Actually, it's 20 weeks of unlimited drainage. And in other words, this circuit that I got from Bewley, L.V. Bewley, that Eric Dollard cites as his initial inspiration back in his high school days. It was an extracurricular reading material, because that's how he learned how to read as a little toddler. His father was an engineer. He just took the engineering books off the shelf and started reading them, and that's how he learned how to read English, was by reading his dad's engineering books. He didn't read Jack and Jill Up the Hill. So that's, I think he's the reincarnation of Steinmetz, if you ask me. Not Tesla. People like to say he's the reincarnation of Tesla. I don't think so, because Tesla was not a true engineer as we know it today. He did do some engineering, but mostly he did simulating in his head, because he had a head for a simulator. Or he had a simulator for a head. However you want to. Plus photographic memory. His sister had photographic memory, and his mom was intuitive. So, or might have had photographic memory, I can't remember. Somebody did a biography of him. Somebody interviewed him, before he died. Um, Anywho, but his simulator in his head was based on his experience, but he did have a simulator for a brain. There you go. And so he could do what I cannot do. But see, that's the way to properly look at Tesla. He was not a fully qualified engineer. Half the time, or most of the time, whatever, he used the simulator in his brain. And so he didn't have to really know what he was doing. And so he could go beyond presumptuous style thinking, habitual style thinking, conditioned thinking. Charlie Lutz would always say we have to transcend conditioned mind and learn to think with our heart. Learn to think intuitively. Learn to make use of inspiration, imagination, and intuition if we want to survive in the coming 2 millennia, because the Aquarian age is an age of mind, and changes are going to speed up. They're going to continue to accelerate. The rate of change in life on this planet is going to continue to accelerate to such a degree that babies will be born who will be 3,000 years ahead of their parents, and their parents are going to have a dickens of a time trying to deal with them. You think my mom had an easy time dealing with me? My whole family thinks I'm schizophrenic. But the problem arises is that I'm about 1,000 years ahead of everybody in my family, or people in general. And it's not until people start to meditate en masse that they're going to start to appreciate free energy, because consciousness and energy are one and the same. I'm not going to get into that. I've already done videos on that topic. But you really have to be a yogi or, a partially enlightened soul. Your heart chakra opens up and you want to share in order to appreciate free energy, because free energy is for sharing. It's not for being charged. And I've heard some horrible stories of J.P. Morgan actually waited until Tesla came to him for help because he couldn't go anywhere else, which probably was a manipulated situation, because J.P. Morgan wanted to manipulate Tesla. He wanted to destroy him. So it wasn't just that, as Eric Dollard says, that Tesla lied to J.P. Morgan by not telling him fully his intentions of what he intended to do with Wardenclyffe, to send free power to everybody on the planet. He didn't tell him that part. He told him that it was for free private communications between any two people on the planet. But J.P. Morgan already knew what Tesla was up to and was fully informed, and just waited until Tesla came to him and probably manipulated the situation so that he would have to come to him for help, and then destroyed Tesla and made sure he was destroyed for the rest of his life. So, this sounds pretty awful, but, that kind of mishigas still goes on. And that's probably why I hesitate to build anything. And you know what? If I did, I probably wouldn't even show you. That's why I called this sight unseen. Because if I ever built anything, I wouldn't show you. I wouldn't dare. I wouldn't dream of it. I've seen to what degree people can destroy my life. So I don't even need to hear stories from somebody else. And not because they were trying to prevent me from hurting anybody, but because they were trying to maintain their own position and reputation and status and nothing more. They were willing to destroy me to maintain themselves. And that's not a way of life that's acceptable to me. It's not. I don't, at least, I try my best not to do that. But, as it's certainly not something I want to try to do. Let's put it that way. It's not something I believe in. But, anywho. So, simulating is safe, that I can share, because I'm just sharing knowledge. At least I like to think so. Hey, if I end up dead and it looks like suicide, you never know. But that's as far as it goes. I won't show you anything. And so I'm not here to prove anything. I'll never try to prove anything to anyone. I don't have to. I was born gifted. I didn't have to prove anything to anybody. I knew that. I have access to stuff that most people can only dream about. Soul memory, it's stuff like that helps put me ahead of everybody. But I don't have a simulator for a brain. But I don't have to worry, because there are simulators all over the planet. And you just pick one which suits you. And this one suits me just fine because it's open source. I can go in and change the code. And there was one policy that Paul Falstad instituted that I had to correct, and only one. He put an arbitrary limit on current surging through and because of a diode or a transistor. And I went in and changed that, and the rest is either window dressing or various improvements to try to help my ability to promote surge-oriented circuits. And, otherwise, I didn't change anything, And also realism. I tried to improve realism to challenge myself. So, but some changes I couldn't make, and so I have to put it in manually. I have to put a resistor alongside a battery. I didn't put any resistor alongside the source here. Maybe I should have. I did put it when initiating the circuit, but there is some resistance in a source current, so actually this resistor here should be raised a little. Oh, let's do that. Oh, raise it. Let's make it 1 milliohm. Yeah, let's do that. And let's save that. Because I like to be realistic. Okay, so there are a few changes. What was the other change I had to make? Well, I'll have to re-watch this video to find out what it was. Anywho, so let's run the circuits. So I'm showing you how to run it. So it comes on, and the first thing you do is you give the circuit a charge. And you don't give it much. You see here, negative 40 nanoamps down here. If we did maximum scale, you see a spike here of negative 40.5 nanoamps, but I usually don't like to have this go maximum scale. Or maybe I should. Then you can see the scale. Well, you see the scale here. This is negative 8 microwatts. So actually, this should have been... Yeah, okay. I'll watch the video and then I'll know what changes to make to this that I told you about. So now you see this. That's how much energy you put on the circuit from the mains. That's how much it costs you. Now we go over to the clock mechanism. And whether or not you see these switches closed doesn't mean they didn't close. It just means the simulator could not display them as being closed. But if you look here, this keeps jumping when it's supposed to, whether or not these close. And so it shows me that the simulator is doing the correct calculating. It just can't display evidence of why it increased the voltage. Now, I increased this cycle time in order for these incremental jumps, increases, to be at a reasonable rate, so that you can fine-tune how much amps you want to deliver back to the grid. Otherwise, you end up with wildly different figures, too much and too little. But I had to do it this way, and so... But it only takes about 2 seconds to reach that point, because, look here, we're not even at 300 milliseconds yet. And we've got a mere 30 nanovolts built up on this piece of wire. Now, we don't have nanovolts on this capacitor, as you can see. Well, no, we do. 30 nanovolts. See? But we go over here, and we have 100. Ooh, we have 200. We go over to the transformer, and we have zettavolts. So the transformers don't exhibit a whole lot of voltage. It's the capacitors that are building up the voltage. So actually, this is telling you the voltage on the capacitors, see? So it isn't just this piece of wire. It's telling you the capacitor voltage, which is what's, where the voltage is being stored. And it's going to be gigavolts, 300 gigavolts to reach my target. Oh, that was the other change I wanted to make. I wanted to change this to 120 volts. So there's all kinds of little changes to make here. Yeah. What can you do? You do what you can. Because I'm doing this on only one branch. Now the circuit is dangerous to work with, but its connection to just one outlet on one branch of your house mains, You know, if you isolate one branch and don't have any appliances on that branch, then you can get away with having this. If you go for moderation, you know, you're not trying to make gazillion bucks, because if you put too much amps back, it's going to trip a relay, a reverse current relay that will shut down power in your entire neighborhood, if not the entire city in which you're at. You know, whatever the substation is in charge of, however much territory, you don't want to do that. You don't want to have a bunch of electric utility trucks show up at your door, because they'll locate you, you know. So you want to be reasonable, and you just want to save on your power bill. And maybe you can put enough back to actually, you know, compensate for what you use. But the problem is, it's not something you can use, because it's going to be, you know, right now you've got nice sine waves, but it's picoamps, because we're not connected. The circuit is not connected to the mains yet. We just did it momentarily to initiate a charge here in nanoamps. But when we connect it using, see, these are momentary switches, these two, for initiation. These two outer switches are not momentary switches. They're, you know, they stay where you put them. And so this is what, these two outer switches are what I'm going to use to connect the circuit to the mains, to drain to the mains. Once I get up to my target of 300 gigavolts, which I have to wait a while in real time, in our time, but only a matter of a couple seconds in simulator time. So I don't bother these are the only things you have to look at in terms of how you're doing. See, now it's already changing color. It's like a light red. So it's showing it's building up a little bit of a voltage charge on the various components. But I had to do it this way because I have to be reasonable. Now the size of the coils on the transformers are just suggested minimums. I found that 99% coupling coefficient was the minimum. That's the requirement. And anything else is really up to you. You know, how big you make your coils, how big your capacitors are. But 99 coupling coefficient seems to be a minimum, because when I had it at 90% coupling coefficient, it didn't work. But 99% worked. So you don't need 3 nines, and 1 9 is not enough, but 2 nines is pretty good. In fact, 2 nines works. So now we're up to 5 volts. We're slowly rising here, and we still haven't even reached a second yet. So you'll see, it takes less than 2 seconds, probably. Yeah, it does. That's right. Now, so I only have a clock timer when we surge to regulate the surge, to prevent us from surging too quickly. And then when I'm done with the regulated surge, I flip over to drainage mode and disconnect the clock. So then all these switches have to remain open all the time. And each of these switches, when they're open, they have 10 gigaohms of resistance. And when they're closed, they have 20 ohms of resistance. Just so you know. Just so you know. Okay, what are we up to? 30 volts. So we're kind of getting there. So we need a lot more than that. We need gigatimes more than that, which is 1 billion. We need 1 billion times more volts than what we just had a moment ago. You know, I mean, how many, you know, it's kind of absurd because lightning is around that in terms of voltage. So you're literally dealing with lightning here. And that's why I make the allusion to my lightning oscillator, even though the lightning oscillator is not realistic. Not only in terms of build, but in terms of, you know, components to build, but in terms of the fact that it operated with 0 resistance throughout its circuitry, which was very unreasonable. But, you know, it was a year or so ago that I developed that, so I didn't know what I was doing. I did the best I could. But it was an oscillator. It self-oscillated. Here, I have to use a timer to regulate the activity of the circuit. But still, I end up with gigavolts, which is what that circuit did. It was mega amps and gigavolts. And that's a lot of voltage. So it doesn't surprise me that I have to do that in order to try to be practical. Some practicality, you know, gigavolts. How practical is that? You know, I can't say it enough that that's not exactly a good selling point to the circuit idea. But I like Bewley's, I like this circuit derived from Bewley's knowledge, because, I don't know, it's just so simple. You know, 4 capacitors and 1 transformer, and I add another transformer to help boost the ability for the thing to surge and to even things out. And this, and these two pair of coils are turned around actually to these two. You know, they go across here. So they're at a different angle. So in a sense, you can't really say this is LMD or TEM, you know, analog computer anymore. It's both. Although the load over here, no, it's both. Well, the load over, yeah, it's a little confusing, but it's a ring is what it is. You've got a ring of capacitors, and outside of which is a ring of transformer coils that are connected together, 4 of them. 4 capacitors and 4 transformer coils. An inner ring of capacitors and an outer ring of 4 transformer coils that are hooked up together. That's what it amounts to. And it's a very interesting concept. It's an archetype. Because it almost doesn't matter how big your coils are or how big your capacitors are. It does matter the coupling coefficient on your transformers, but that's about it. You know? The rest you can change any way you like, whatever you want. Do whatever you like. You know, you don't have to do it this way. This is just an example of what could be done with this basic archetype. I love archetypes because it makes things so simpler for me. I'm not an engineer. I'm just a tinkerer. And I monkey around like Edison would do, you know, monkey around, try this, try that, because I don't know what I'm doing. But I know to follow in whatever small way in, you know, my tiny little footsteps inside of Eric Dollard's very large footprints, because he knows what he's doing. Now you see it jerked there up to a gigavolt for a moment there, I saw. Yeah, just for an instant. So you see we're already almost there, sort of. But it has to be stable. You know, when you look at the circuit, how it behaves, it has different levels of charge based on various changes you make, you know, in operating the circuit, what switches you throw. And you'll go back to that level. So it's interesting, different states of charge. But we want to reach 300 gigavolts, at least I do. Well, here's 300 megavolts. Yeah, I think Eric Dollard is a reincarnation of somebody like Steinmetz, because he's really a par excellence engineer. Yeah. Yeah, Tesla was a bit of a dreamer, a bit of a tinkerer, a bit of a dreamer, but he had a simulator for a brain, and that made it easy for him to come up with stuff that nobody would have thought of, because he could just simulate it and see how it runs. You know, he didn't have to engineer everything, unless he had to. Right? So he only engineered when he had to, but the rest of the time he could simulate. And isn't simulating a lot easier, you know? I think it is. Engineering acumen actually helps, obviously, but it can hamper you if you're too much into engineering. There, 245 gigavolts. So I turned off my connection to the clock, and now it's stable, so now we connect it to the grid, and what do we have? Oops, it's positive. Now why did I... Oh, because I made changes. Oh shoot, I'm sorry. Anytime I make changes to the circuit while it's running, it flips the polarity of the voltage. So just imagine this is negative 12 amps being returned to the grid, as opposed to positive 12 amps coming from the grid, because I didn't intend it to be this way. But that's the caveat of doing it this way. Here. Well, take my word for it. Oh, God. You know, why should you take my word for it? All right. Let's reset this business here. I'm sorry. I shouldn't have made changes while I was running the circuit. That was really a mistake of mine. Charge up the circuit. Started going. So we've got nanoamps here. 9 nanoamps. No, we got 9 nanoamps. Positive? Oh. See, now the voltage is positive. So at some point I wasn't paying attention. This went negative. It was probably when I was changing this resistor over here, maybe. That's usually what happens. So we'll just... actually, no, you're not going to be able to... Oh God, I got to start all over again to show you for real. Well, why not, you know? Hey, this is fun. We got nothing else better to do. Why not? I got nothing else better to do except upload a very big video to Vimeo. Uh, so it only cost us 10 nanoamps because the way I flicked the switch was very... Oh, no. No, not the way. It's because I put this resistor here. I raised the resistance to 1 milliohm. So now it's going to cost us a mere 10 or so nanoamps to get this thing started. So I'm very cautious. I try to be very cautious in that respect. But I also have to have this here to show that this has some internal resistance. I had to put a reality checker. Actually, that's the reason why I raised this. Because in LT-Spice, you can put equivalent series resistance inside the component itself, certain ones. And, you know, I don't know how to do that in Paul Falstad Simulator. I managed to do it for coils and transformers, and for capacitors. But, you know, my ability for Java programming is very limited because I'm not trained. You know, I just kind of monkey. You know, I'm a monkey. I monkey around with things. But I come up with stuff because I'm willing to, because I want to, because I believe it's true in my heart. And then when I have these successes, then I go to theory to look for confirmation. But again, any simulation is part make-believe, part reality, because we don't have a simulator for a brain like Tesla. And even Tesla might have made mistakes, you know, because even his simulator in his brain may have certain oversights or undersights, you know, in which he had to eventually go and test the thing out on the bench. But at least he had people working for him. He had money coming in, you know, when he did. So he could build stuff, scale it up, whatever, and see how it actually works in principle. And, you know, he did demonstrations and actual experiments because he knew the true satisfaction is building it. Everybody knows that. But I'm not a builder. I'm not mechanically inclined. I'll take a clock apart and I won't be able to put it back together again, you know, because I don't pay attention to those things, all those little details. And he had photographic memory, so he could remember exactly how to put that clock back together again. So he was very mechanically inclined, even though he was focusing his efforts on electrical engineering. But he had a simulator for brain as well. So he had all the tools necessary to be an innovator. And all I have is wishful thinking and a simulator to help me and Eric Dollard to serve as a role model to some degree. So, you know, I've got all these assistances, but I don't think Eric is a reincarnation, you know, of Tesla 2.0. I don't think so. He's more like a Steinmetz because he's more like a traditional electrical engineer. It's just that he's born with it already, you know, reading his father's engineering books, you know. It could have been a more appropriate birth, even though his parents kind of kicked him out at the age of 16 because he blew up his parents' garage with his experiments and disrupted the neighborhood with all the static interference that he was creating. But he did have an acumen. Yeah, I'm sure. I'm sure he was born with the gift, you know, from prior experience. And Steinmetz would be a perfect choice, a candidate, you know, as to, you know, where is Steinmetz today? Well, he's probably Eric Dollard, you know, because it's somebody like Steinmetz who's walking around in Eric Dollard's body, because that's the kind of giant of an electrical engineer that Eric Dollard is. But I don't think he's a Tesla. Tesla was a dreamer. And Eric has described him as such. And when I look at him, that's what I see. But he could dream because he had a simulator for a brain. He could get away with it. He could get away with it. You and I can't. We have to, you know, turn our attention to a simulator if we want to dream. Because that's the only way we can dream. I mean, you know, otherwise, when I was 5, I imagined, you know, plugging in a wire in the outlet and then quickly unplugging it and plugging it to the other end of the wire, and then I have free energy, eternal energy, immortal energy running around in a loop of wire. It's a nice idea, but that was the best I could do as a 5-year-old, So I'm still doing the same thing. I'm just a little more sophisticated, hopefully a little more accurate to reality, hopefully. But we'll never know, right? If nobody builds this, and if I don't show you if I built it, you at least will never know, and I will never know if I never build it. But I would never try to show anybody. There's no point to showing off to make that would be ridiculous. It's like waving a red flag in front of a bull, a hungry bull no less, a hungry bull who was didn't get a good night's sleep last night, I mean, or was constipated or something, I don't know, who had a falling out with his lover, I mean, that's, in today's world, jealousy is rampant, and the violence that goes with jealousy, so why would I want to attract attention? I've already done so. I've already been the activist. I'm 61 years old. I've done enough activating for one lifetime. So all I can do now is dream and try to inspire you with my dreams. And I'll leave it at that, because that's semi-safe, If you don't want to build this stuff, that's your business. It's none of my business. It won't help me any. Nobody's going to make money off of this. Trust me. You won't survive. Your company will become bankrupt before you even begin. Trust me, it happens every time. They don't have to murder anybody. It's real easy. Just bankrupt you. Or ignore you, and you get swept aside in the tumult, in the run of life. You'll just get swept aside. So many inventors, that's all that happened. A few got murdered. Yeah, we know about that. But most of the time, people just get forgotten. They get swept aside, and bankruptcies happen too. I can name a few, but I can name one, but I don't need to. It just happens, because there's a lot of jealousy, a lot of stiff competition to maintain things the way they are. So keep it to yourself and share it with a few of your neighbors and leave it at that, Don't try to think, I'm going to save the world and I'm going to make lots of money. Those are people who are, I don't know what they don't study history. So how can they study free energy? Because free energy is in our histories. People in the time of Steinmetz knew about this, but we don't now because it's been suppressed for the last 100 years. So you have to go back and study history to actually believe in this. You have to be into old stuff to be able to be interested in free energy. You can't be into modern stuff, because modern stuff you're not going to find it. It doesn't exist in the modern world. It's been suppressed very efficiently. But only for about 100 years. Prior to 100 years, it was ripe and fruitful. So you have to be into studying history. And so if nobody studies history, what has happened to inventors over the past century, whenever they came up with anything, then of course they're going to make statements with, how come you're not building something? And don't you want to make a lot of money? Prove it to us, because we know it's not going to work, but prove it anyway, build it anyway, and it's like it's really there. I don't have to give my opinion of what I think of that kind of attitude. Anyway, yeah, it's anybody who's studied the history of anything over the past century within our socially engineered society, because I've already done this in other subjects. Studied what other people have learned by studying history without me having to study history. They just without me having to lead the way. Other people who lead the way, who've studied history, who have seen the changes in society early on in the early few decades of the 1900s. It's all over the map. The engineering of society has been happening on many levels, but we don't know that because that's nearly a century ago that it all transpired. So how would anybody appreciate it, So now our voltage is positive, which was what we want. That'll send negative amps back to the grid. So I'm just waiting for it to reach 300 gigavolts. Meanwhile, I had all this time to yada yada some more. See, despite all that megavolts, all we have are milliamps, so, you know, that's not exactly what we're shooting for. That's not our target. But it'll last you 20 weeks before you see 4% of change of drainage if you're feeding 15 amps DC back to the grid. Now, I don't know if we can get away with that. See, that's another thing. I don't know if we can get away even with even a mere milliamps of DC being... Well, see, that's the problem. You have to have a certain minimum voltage to be able to send anything back to the grid, or else the thing doesn't work. You'll get these wavy lines. These wavy lines down here, instead of instead of what we want to get, which shows that, you know, we're contributing to the grid instead of just being submissive to the grid. You know, we're taking a command position. Well, you have to have a lot of volts built up to do that. So there is a certain minimum, and we don't have to be a substation. Well, no, with this much gigavolts, yeah, we are operating like, not like a substation, more like a power plant. All right, 300 is the target here. I'm waiting, I'm focusing. Stop, yada yada. Okay, 100, 160. 170, 180, there, 290 gigavolts, just to get nearly 14 amps negative to go back to the grid. So that's within the limit of my circuit breaker, right? Circuit breaker on a branch circuit is 15 amps, or actually it's 20 amps, right? On a branch circuit, say if you pick one outlet in your home, that branch circuit has a 20 amp breaker that it goes through, but the rating of wire is 15 amps maximum. You know, 20 is the safety limit, but 15 is our end safety limit, so that's why I try to keep it under 15 amps, and that's why I went to a lot of trouble to fine tune this so that I could get to this. Now let's stop this and turn the time step into a 100-second time step and see what happens. You're going to get a change down here. It's not going to be 13.83 negative amps, but be that as it may, it's going to be slightly different, but it won't be too different. But I'll get to show you. Now I got a 100-second time frame, and it took 1 3/4 seconds to reach this point. Okay? Less than 2 seconds. Now, how long does it take to get an appreciable change? 22.42 amps. 22.42. How long does it take for it to begin to drop? %1 of an amp. Takes a while, huh? Told you so. That's the other difference. Ah, there. 842 kiloseconds. 842 kiloseconds. So, 842 kiloseconds divided by 3,600 kiloseconds is 1 hour. 234 hours divided by 24 hours in the day is just under 10 days. So I said 2 weeks. It's really a week and a half. So it takes a week and a half for any appreciable loss to arise. A week and a half for 1% drop in amperage. You know, that's considering the fact we got 300 volts. Over 300 volts. Over 300 gigavolts in these capacitors. Look at this. We've got terawatts. Oh my God. We got gigavolts. Yeah, the power rating is terawatts. We got gigavolts. We got gigavolt. We got gigavolt. We got gigavolts. Now in the transformer we have microvolts. No big deal. So you don't have to worry about the transformer coils heating up. Yeah, the amps are small, the volts are small, microvolts. It's the capacitors that are going to be storing all the charge, and the wire that carries it. The capacitors are going to be a safety hazard. They're going to be a risk. But what we get coming back here, we've got millivolts and 22 amps. Millivolts, you know, nothing to worry about. Millivolts adjacent to our power source. If we look at the switch 22 amps, millivolts, 2 millivolts. So, you know, it's the capacitors that are going to be dangerous, and some of the and some of the wire and some of the connections leading, you know, directly to the capacitors, or I don't know. In this case, I don't know. I guess it's going through this switch. Yeah, see, the switch has gigavolts. So every time these switches open and close, you're going to have a huge arcing problem. And there's a way to suppress that. Paul Falstad shows. He shows it. Let's see, where was it? Was it diodes? Or was it capacitors? No, was it transistors? Oh, blocking inductive kickback. Yeah, it's the blocking inductive kickback that he uses to regulate, to quench, I think, arcs. Anyway, something like that. Actually, no, wasn't it under capacitors? Oh, see, yeah, it was under other passive circuits. He also had blocking inductive kickback. Well, here, let's just go find out. I'm trying to show you what I'm talking about. Alright, so where other? So he put a capacitor across the switch, which is pretty smart. You know, I didn't do that here. Maybe I should, but I'm afraid it'll change the operation of the circuit, so I don't. You can do it if you like and see what happens, but, well, why don't we try that? I can't do it with a toggle switch, though. See, I use toggle switches here because I can do 2 switches at once. I can't do it with a singular switch. Oh, I know how I'd do a capacitor. I would draw it across. Yeah, let's try that and see what happens. If it works or not. Okay. Oh, see, it goes right through. Yeah, it doesn't work. It won't work when it's needed, unfortunately. And for initiation, it won't matter because it's low. So it won't work when it's needed. It's needed out here on these outer switches. It's not needed on the inner ones because that's initiating from a cold start. So it's not gonna. There's no risk, you know, on the inner switches. But on the outer switches, you need it, but it leaks. It goes right through. So it leaks in the sense that, you know, one side is getting charged and the other side is discharging at the same time, which makes it look like current is leaking through. But whatever, you know, you get my point. So that's not going to work. See, we can't do that. Unfortunately, we can't save the day. So we're going to have massive arcing here when we close the switch. So there has to be some other mechanism employed to prevent that problem from arising, so we don't have problems. Now I've wiped out the voltage waveform, and I'm not sure how I managed to do that. The voltage is now 3 volts. Yeah. So I don't know how well this circuit is going to work if you keep monkeying with it. Well, no, I made changes. I added these capacitors. So I think that's what happened. I think that's what's happened. Because if I reset it, oh dear, what happened? Oh my god, I really messed up. I'll be darned. Oh dear, I lost the waveform. the voltage waveform. Why did this die? Why did it die? Go figure. It just died. There's no power coming out of this anymore. That's weird. I wonder why. Oh well. I'm not going to worry about it now. Oh well, that's the end of my video. I've shown you everything I wanted to show you, and I don't know. See, that's one of the problems I'm having is reusing the circuit if I do something wrong. Apparently, I don't know what wrong I'm doing, quite frankly. Maybe I should put this resistor on the opposite side. You know? I'm putting it on the hot side, but I could put it on the neutral side. Oh, I see why I did that. Because that was... Okay. So I have to... do this. And then put this down here. Let's see, where can I get a resistor from? No, I don't know. Oh, here, we'll use this one. Whoopsie. Come on, move over. It's still, I lost it. No, I don't know what I'm doing. Oh well, anywho. So that's the end of my video. Now I gotta stop talking.